Hello everyone. In this video I'm going to walk through the Chapter 5 Test 1. So this is the practice test for Chapter 1 that's required. So in this first example here we're looking at a meteorology student who wonders if her predictions of the local weather are accurate. To assess accuracy, she looks at her predicted high temperature each day for 1 month and records the actual temperature each day. She then computes the difference between these two values by subtracting the actual temperature from her prediction. So if the weather forecast that she has is accurate, she would expect the average difference to be close to 0. She'll get positive numbers when she overestimates the temperature and negative numbers if she underestimates the temperature. So you're going to need to open up the data file in Jamovi, and I already have it loaded up here and I have the difference scores. So the further the score is away from 0, the more she over or estimated the temperature. Okay. So our very first question asks about the assumption of normality. So the assumption of normality, remember, is looking at the distribution of sample means, where this assumption is that the distribution of sample means is normally distributed. And we know it'll be normally distributed if the population of scores is normally distributed or the sample size is sufficiently large. So by sufficiently large, we mean over about 30. Right? So we don't know what the population of scores looks like, and graphing our scores isn't going to help. So what we are counting on is the central limit theorem telling us that our distribution of sample means will be normally distributed if our sample size is sufficiently large. Our sample size here is 30, and so that's large enough for us to think that we're going to have a normal distribution. Okay, so moving on to question 2. We're going to create a graph of the data, and based on the graph, does it look like her predictions tend to overestimate or underestimate the temperature? So I'm going to click on Exploration and click on Descriptives. I'm going to move that difference score into the variables box, and then I'm going to ask for a graph. And so these are different scores, and I'm going to create a histogram because they're continuous variables where fractions make sense. Okay. All right, so if we look at our data here and create a graph, look at our data, we have our graph here. And we can see that our scores are, here's the 0 point. These scores are higher than the mean. These mean that she overestimated the temperature. Or I shouldn't say higher than the mean, higher than 0. They mean she overestimated the temperature. And these mean that are below 0 mean that she underestimates the temperature. When I created this, I also obtained a list of descriptive statistics. You can see that our mean is negative 0.43. Right? So it's looking like she probably tends to underestimate the temperature a little bit. All right, next, moving on to 3, select the correct two-tailed null hypothesis for this study. So in this case, we would expect that if the null hypothesis is true, and in fact she can accurately predict the weather, we would expect the mean to be 0, because we're looking at how far she is away from those, the actual prediction, or her prediction and the actual score. We'd expect that difference to be 0 if she's accurate. So that would be the mu for the population mean is equal to 0. Right? It's a mu because we're trying to make an inference from a sample statistic, that sample mean of negative 0.43, to the population parameter. All right, so question 4 asks you to compute the average difference between her predictions and the actual temperature. So we've already done that. We have our average here. This is our mean of negative 0.43. That was the average for her differences there. Number 5, in this research situation, which value are you comparing the sample mean to when you use a single sample t-test? So in this case, we're going to compare it to 0. Right? So we want to know if her difference is different than 0. Okay, now we want to compute the estimated amount of sampling error in the study. To do this, we're going to need to compute a t-test. So I'm going to click on t-test, one sample t-test, and our dependent variable here is the difference score. It's our only variable in this data file. And we're going to do a two-tailed test, you can see right here, and our test value is 0. We're comparing that mean difference score to 0. So we're also going to ask for descriptive statistics. We're going to get a mean difference with the confidence intervals and an effect size with confidence intervals here. Okay. And that will be what we're going to interpret here. Okay. So this question asks us about the amount of sampling error. And the sampling error is the standard error of the mean. It's abbreviated here SE, which is the standard error. And for this example, our standard error is 0.96. That is the typical distance we would expect between sample means and the population mean. Number 7, we ask you to use the software to compute a single sample t. And that's already generated here in your Jamovi output. All right, so our single sample t here, our t-statistic is negative 0.45, right? It says students t and then statistic is what we're going to analyze there. Okay. All right, then moving down, we want to know the two-tailed p-value. Now we know we're going to get the two-tailed p-value because under the hypothesis test, we asked for a two-tailed test. The not equal sign means a two-tailed test. When you're using the greater than or less than sign, that would mean a one-tailed test. So we can get our p-value from our output right here. Right? So our p-value is 0.65578, right? Or 0.66 is our p-value. All right, next question is, what is the standardized effect size D? Right, so this is in our output. If we scroll over, you can see the standardized effect size is Cohen's D here. It's negative 0.08. Right? So we could have also looked at the mean difference as a measure of effect size. The mean difference is she is off by negative 0.43 degrees, or that gives us an effect size of negative 0.08. All right, moving down. Number 10, use software to compute the 95% confidence interval around the mean difference. And that is listed right here on your output. The 95% confidence interval around the mean difference is the lower bound is negative 2.40. The upper bound is 1.53. So I'm 95% sure that the true mean difference is somewhere between negative 2.40 and 1.53. When I say the true value, what I mean is the population value there. Okay. All right, moving on to number 11. Now we're going to compute the 95% confidence interval around the standardized effect size. Okay. So around the standardized effect size, you're looking for the confidence interval around D. Now to get this, I'm using Jamovi to get it. Some software actually doesn't provide the confidence interval around D, but we do have it here in this. Right. So here, if we're looking at our confidence interval around D, scroll over. My effect size is negative 0.08, and my 95% confidence interval is negative 0.44 to 0.28. So I'm 95% sure that the true effect size is between negative 0.44 and 0.28. So it's somewhere between, if I'm looking at 0.4, that's almost a medium effect. 0.28 is kind of a small effect. But note they're in opposite directions. So it's a medium effect for underestimating and a small effect in this direction of overestimating there. All right, now, in order to choose the best APA-style summary of the results, what we need to look at here are several things. The first thing is the degrees of freedom. So our degrees of freedom are 29, and so that is the number in parentheses. Right? So For this one, the obvious answer is it has to be the first one, but let's walk through where all the numbers come from. The t value itself is negative 0.45, which we get from right here. The p is 0.66, which I get from right here. The 95% confidence interval around the mean difference, you get here. The effect size d, right here. And then the 95% confidence interval around the effect size comes from over here. All right, number 13. I want you to fill in the blanks for the summary of the results of the single t and the effect size. Right. So our mean difference is negative 0.43, which means that the student tended to underestimate the temperature, and it's by a small amount. Our effect size is small. And now we want to know, is this difference likely or unlikely to be due to sampling error? Right. Now I realize I'm sort of using dichotomous language here, but it's just because this is a multiple choice question and I know that my p-value here is 0.66, which means it's really likely that the difference is due to sampling error. Okay. So this outcome is very likely to occur even if the null hypothesis is true and she makes accurate estimates. All right. So when we're interpreting the p-value, I want to know what's the best interpretation of a p-value. And so for our p-value, the closer the p-value is to 0, the less compatible the data are with the null hypothesis. Okay. Or another way of thinking about this is the closer the p-value is to 1, the more compatible the data are to the null hypothesis. Okay. We're not making a judgment about whether or not the null hypothesis is true or not, just whether or not our data are compatible with it. All right, number 15. Suppose you computed a two-tailed single sample t and obtained a t of 2.05 with a p of 0.04. And so what is the best interpretation of the p-value? So what our p-value is telling us is the probability that I would get a t as extreme or more extreme than an absolute value of 2.05 if in fact the null hypothesis is true. All right, so I drew a little picture over here on the right hand side, and this is a distribution of sample means assuming the null hypothesis is true, and these are t-scores in this distribution. So we obtained a t of 2.05, and so that t gives us a p of 0.04 in total. There's 0.02 on the right side and 0.02 on the left side. Right? So the probability that I would get a t that's greater than 2.05 or less than negative 2.05 is equal to 0.04, assuming that the null hypothesis is true and there are no methodological flaws in the study there. All right, now if we're looking at a standardized effect size for a mean difference, the standardized effect size that we're working with is d. Okay, so d, the way we compute it is we take the mean and divide by the standard deviation. Right? So I take the mean difference actually and divide by the standard deviation is my formula for d. So what we're doing is taking that mean difference and dividing it by a standard deviation, which puts the mean difference into standard deviation units. So like a d of 0.2 means that somebody is 0.2 standard deviations above the mean. A d of negative 0.8 means that this mean is 0.8 standard deviations below the mean. Number 17, choose the best interpretation of a confidence interval. Okay. So a couple of things to note here is that when we're talking about confidence intervals, we're talking about estimating a population mean difference. Okay? So in this case, the correct answer is it's an estimated range of plausible values for mean differences in the population. It is not an estimated range of plausible values for mean differences in the sample. We already know what our sample data are. Also, it doesn't tell us how likely a study is to be replicated. You don't get that information from the confidence interval that way. Number 18, what can you do to make confidence intervals narrower or more precise? So when you're thinking about confidence intervals and how to make them more precise, if you think about it, your confidence interval is going to be a point estimate, and then you're going to add and subtract a margin of error to and from that, right? And my margin of error is going to be a t-statistic multiplied by the standard error of the mean. The t comes from a table. The standard error of the mean is the standard deviation divided by the square root of n. So this whole unit here is our margin of error. If I want there to be a narrower confidence interval, what I want to do is make that margin of error smaller. And the way I make that margin of error smaller is typically by increasing n, right? So if n is bigger, that standard error is going to be smaller, which is going to make my confidence interval narrower. Okay. Next, moving on to number 19, we have here the scientific literature suggests that people often overestimate their own qualities and ability in a wide variety of contexts. A student wonders if people overestimate how lucky they are. To test this, the student asked 50 students to complete a scale that measures how lucky people believe they are. The scale consists of 10 questions with a 5-point response scale, where 1 equals much less likely than other people, 3 is about as lucky, and 5 is much luckier. Scores on the questions are average for each participant, and they want to know if participants' mean scores are higher than 3. So 3 is the midpoint of the scale, which makes it sort of a natural comparison point. Do people think they're more or less lucky than other people? And so we're going to compare them to 3. All right. So the first question we have here is, we conducted a single sample t-test comparing the average luck rating to blank. Right? So we have all these data here. What we're going to do is compare the average rating to 3, right? Because that's what was said in the question. That was the context there. All right. Now we're asking you to choose the best summary of these data. So let's go back and look what we have here. We can see that our p-value is 0.6, two-tailed, which suggests that this difference we're observing between 3.06 and 3 is probably just due to sampling error. The d is 0.08. Right? That d of 0.08 tells us that it's a very small effect, negligible effect that we're looking at. So the observed difference we have is probably just due to sampling error, and it was also a small effect. So when we're looking at this, people did rate themselves as luckier than average. It was 3.06 rather than 3. Okay? So we're going to choose one that says they are luckier than average. So B is luckier than average. But we're pretty sure this result was due to sampling error. And so we're going to withhold judgment on the difference, maybe replicate the study to see what occurs. 21. So our effect size was, when we're looking at the mean difference in raw score units, was 0.06, right? This was a really small difference, right? So we're looking at the difference between people's ratings of their luck and 3. That difference was 0.06, and that's a really small amount on a 5-point scale. For 22, we're looking at choosing the best summary of the scientific context. Right? So in this case, in the problem, we told you that there is research showing that people overestimate their own abilities, and so we're going to pick one about people overestimating their own abilities in here. But note that our study isn't consistent with this, right? There were no consistencies here because we didn't find any evidence that people overestimated their abilities, right? Our p-value suggested the difference we observed was probably just due to sampling error. Okay? So our study is not consistent with the existing literature showing that people overestimate their own abilities. We also don't have any information about methodological flaws in the study, but we should probably determine or replicate the study to determine if there are any issues there. Okay. Now, the question we have here is, are there any problems with sample size in this study? So if we go back and look at our sample size, we can see that our sample size was 50. We had 49 degrees of freedom with a sample size of 50, which is fine, right? That is not an overly small sample size. So the last option is not correct, right? So the assumption of normality is probably not violated because our sample size was at least 30, right? The study should definitely be replicated, but not simply because of sample size. Just because generally it's a good idea to replicate studies, right? But what we need to know is, why is this study not consistent with the other literature? All right, next we have the same basic idea with people have a tendency to overestimate their own qualities and abilities. And here a physician wonders if older people with stage 4 cancer, and so this is a cancer that is spread throughout the body, think that they will live longer than the average patient with this condition. So to test this, the physician informs patients with stage 4 cancer that the average number of years people with this type of cancer live is 1.7 years. And then later asks the patients with this cancer to estimate how long they think they will live. And so here are the results. Okay. So we're asking you in this question, we conducted a single sample t-test comparing the average number of years people thought they would live to what? Okay. And we're going to compare it to 1.7, right? So we're comparing our mean value, our mean is 2.8, and we're comparing that to 1.7. So people did say that they believed they were going to live longer than average, right? The difference here that we're looking at is they thought they would live 1.8 years longer than the predicted 1.7. Our effect size in standardized units is 0.65. Now if we look at our p-value, our p is 0.006, which is very low, which means the data are not consistent with null. This is strong evidence against the null, suggesting that this difference is not due to sampling error, that people do have a real bias. Okay. So on average, people thought that they would live 1.1 years longer, right? And then the question is, how large was the effect? It was 0.6, which would be a medium-large effect. Our next question here is about the 95% confidence intervals around the mean difference and the effect size. So let's go back and look at those differences real quick here. So our confidence interval around the mean difference is 0.35 to 1.85. So we're 95% sure that the true value is between 0.35 years and 1.85 years, which is a pretty big difference, right? The D here, our effect size, is 0.65 with a confidence interval that ranges from 0.19 to 1.11. So our lower bounds in both of these cases are very low, right? A difference of 0.35 years is not unreasonable in terms of thinking about how much people are off by their estimates. And an effect size of 0.2 is quite small. So if we go down back to the question, we're looking at very wide confidence intervals. So that knocks out the bottom two. The bottom two are talking about precise and narrow intervals. The top two are asking, they both say that they're very wide, and this could be that we have a very small effect to a very large effect, which are pretty different scientific conclusions, right? People could be off by 0.3 years to almost 2 years. So these are really imprecise values. So I would choose number 1. Number 2 is wrong because it says that these results are due to sampling error, and that's not what the confidence intervals tells us, right? We are saying that the actual effect size could be small to large, but that second half of the sentence is not correct, or the statement is not correct. All right, so in terms of number 26, we want to choose the best interpretation of the confidence intervals. And so we're saying that our effect size could range from small to very large. And so small to very large is correct, but then it says all of these effect sizes are equally likely outcomes in the population. And that's not true. The outcomes closer to the middle, closer to our estimate from our effect sizes that we computed, are more likely. They're more plausible outcomes. Okay? So we're looking for one that this is not correct. Our next one says the effect size in the population may range from medium to large. That's not correct. And it also says that all effect sizes are equally likely outcomes in the population. The third one is the effect size in the population may range from small to very large. However, the best estimate is the medium-large effect, and it's likely that this effect size would have practical implications, right, having a medium to large effect. Right? So this is the correct option. The next one is not correct because it says the best estimate is a small to medium effect. And that's because our effect size was not small to medium, right? Our effect size was D of 0.65, which was medium to large. All right, so moving down now to 28, we're looking at picking the right statistic. So we have three options right now. We have Z for a single score, Z for a sample mean, and the single sample T. All right, so here we have a psychologist examine the effect of chronic alcohol abuse on memory. In this experiment, a standardized memory test was used. Scores on the test in the general population form a normal distribution with a mean of 50 and a standard deviation of 6. We have a sample of 22 alcohol abusers, and they have a mean score of 47. So we want to compare our sample mean of 47 to a population mean of 50. So since we have means, right, we're comparing a sample mean to something, it's either going to be the Z for a sample mean or the single sample T. The way we distinguish between them is whether or not we have the population standard deviation. In this case, we do have the population standard deviation, right? It's 6, right? So our population standard deviation of 6 tells us that we should use the Z for a sample mean. All right, moving on to question 29. A fast food restaurant advertises that a small order of French fries contains 320 calories, and so a nutrition scientist wonders if this is true and purchases 10 orders of fries. He takes the orders back to his lab and measures the number of calories in each order. He finds that the average is 380 with a standard deviation of 50. What statistic should he use to determine if the actual number of calories in the French fries is greater than 320? Okay. So he does have a sample with a size of 10, and he's comparing that sample mean of 380 to a value, which is 320. Note that we do not have a population standard deviation. Right, so this is a single sample T problem because we have a sample mean from a sample size of 10 that we're comparing to a value of theoretical interest. Right, and we do not have a population standard deviation. Question 30, a researcher wants to know if people over or underestimate the percentage of people living in poverty in her state. To assess this, she asks a random sample of 200 people to indicate the percentage of people they think are living in poverty in their state. They reported an average of 5.2 with a standard deviation of 6.1. The actual percentage of people in poverty in the state is 12. So we want to compare a sample mean to this population mean of 12, but note that we don't have a standard deviation of the population. Since we don't have the population standard deviation, we have to use the single sample T. Question 31 is our last one. Scores on a math test given to incoming college freshmen form a normal distribution with a mean of 50 and a standard deviation of 10. A college counselor knows that people who score below 39 need to take a remedial math course before pursuing college-level math. What statistic should he use to determine what percent of students will need to take this remedial math course? Right, so note here that we do not have a sample mean, nor do we have a sample size. We're just trying to locate one score, and that's a score of 39. So that's going to be a Z for a single score. And that is the end of the practice test for Chapter 5. I hope that helped.